Okay, everybody, here we go. All right, so last time we learned how to write electron configurations. Hopefully it's something you're feeling better about. I apologize that the answer link wasn't working. I'll get that up today in case you try to check your answer, so you can make sure you're doing it right. Okay? Yeah, sorry about that, Ben. Let me know. I'll get it fixed today. Take care of that. Yeah?
Sorry, where are the answer sheets located?
So on the Canvas day-by-day page where it says like what your homework is, right next to it is where I leave the answers. So, now with electron configurations, the ground state electron configuration, that's what you guys have learned. That is if everything goes in at the lowest energy level possible, that's considered the ground state. So ground state is the lowest energy for all electrons. Okay, so we even do, let's do that manganese one as an example, Eli. So there's one on your quiz, and I apologize that you may not have known what to do, but it's okay. You're great on participation, just completing it. Okay, so the ground state for manganese would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and the goal is to be able to do these like fast. The more you learn the pattern, you should be able to do it just like that. Now, when you get the end, now I have to count. So manganese is here, so 1, 2, 3, 4, 5. So 3d5 would be the end. Okay, that is the ground state. Okay? Yeah, Eli.
So on the quiz, it was written out like with the 3D.
Yeah.
Do we have to do it like that? Or
So with the ground state configuration, it kind of just depends on who you talk to or what book you read. Sometimes people will write the ground state, even though the 4s fills up before the 3d, they put it in number order still. I like to just write it in the order I fill, because it just makes sense. So you can do it either way. Does that make sense?
It's not technically wrong if you do it like
No, so how they had it was 3p6, 3d5, 4s2. That would be the same thing. Okay? But yeah, either is correct, Macy. Okay, now an excited state is when energy is put into the atom. Now the energy can be put in various ways, right? There's different forms of energy. You can use heat or electricity or something like that. If you put that into the atom, so energy is put into the atom, and some of the electrons can move up. Now, the thing about an excited state is something cannot stay in the excited state forever unless you constantly are giving it energy. Once you take the energy away, the electrons will fall back to the ground.
So one of the questions on the quiz was like the quantum energy, or like which one is, it was something like that, where it's like which one is emitting?
Yes, which one is most likely to emit?
Is it like more of the excited?
That's pretty much saying which one is excited. Because something that's about to emit means it's in an excited state, so it's about to fall down and emit in the process. So yeah, good connection. So an example of an excited state for manganese, so I'm keeping the same element all the way across, is it could look something like this. So 1s2, 2s2, 2p6, 3s2, should have picked something shorter, 3p6, 4s1, 3d6. And there are lots of variations of an excited, but the way to identify an excited is you'll have jumps. Things that aren't filled because the electrons have energy and move up. Okay? Now, an ion state is when an atom has gained or lost its normal number of electrons. Whoa, losest. And that's where we get the charges. So for example, if manganese were to have a 3+ charge, its configuration is going to change because a +3 charge means what? Good, so we lost 3 electrons. Now here's the interesting thing about losing electrons. You don't lose electrons in the same order that they gained them. So when we gain electrons, we go in this order. When you lose electrons, you go from the highest number because it's now about distance. So this is my normal one, and we need to take away 3 electrons.
You take away the 4s.
So these ones get removed first. Because 4 is the highest in number, so that's my actual valence shell.
So that's
So we need to take away 3.
Why does 3D5 have a higher energy state if it's not farther away?
Interesting, huh? So there's a difference between energy and distance. Distance-wise, the 4s is farther away, but energy-wise, the 3D has more energy. So, good connection. So we're going to take away these 2, and then what would be the, so this is, if you want to make note, so this is the farthest out, or the actual valence shell.
and then it's 3D.
Now we can take it from the 3, because there's no more 4s, so then you just go to the highest of the D, which would be the 3D.
I'm
Yeah, Sam.
confused. Isn't the 3D farther than D4S?
Yeah, that not a bad thing to say, but that's kind of what Calvin was bringing up, is it's not so much about, it has higher energy, but distance-wise it's actually closer. So, kind of weird, because it's like you get a little bit of a flip. So the answer would be 2p6, 3s2, 3p6. The 4s is empty, so we don't write it, and we'd have 3d4. Yeah, Eli.
So if it were for the opposite, so let's say you had a manganese, but it had a negative 3 charge, would you add on to the 3D, so it'd be 3D8?
Oh, good question. So when you're adding, you add to the highest level that has room. So in this case, to add, the D is the only one that has room, so that's where you would add it. So good question though. Yeah, Connor.
So why is the 4s the valence electron instead of the 3D?
Because valence purely is referred to by the distance from the nucleus.
So having a higher number means you take from it first.
Yes.
Okay.
Yep. Perfect connection. Any other questions on that? Okay, now let's talk about, this is the cool part of like the science behind how we know this actually is a thing. Like this isn't just a theory that someone came up with and it sounds like it's right. We have experimental evidence that actually shows these sublevels exist, and that is known as photoelectron spectroscopy. Okay. So the idea of how photoelectron spectroscopy works, everybody, is the idea of we're going to put energy into our atom. And what did we say happens to the electrons when we put energy in? They move up. Now, this is the fun part. If you put in a whole lot of energy, you can rip them off. So literally the way this machine works is it rips the electrons off of an atom completely. We strip all the electrons off. In a sense, we're not going to talk about it, but that's what, and then it turns into plasma. Plasma is when you've ripped off all the electrons and it falls apart. Yeah, Matt.
I just wanted to let you know that it says it has so much energy it will remove electrons.
Well, that's good English, isn't it? Have I ever given the disclaimer that I don't teach English for a reason?
Well, I'm just saying, just so you know.
Okay, I'll go and fix it. Thanks. Yeah, Macy.
So what are the uses of plasma? Is it just for like this specifically, or like are there specific uses?
No, this just like results in plasma. We do this to learn information about the atom, but then, yeah, plasma is just made from it. So, good question though. Okay, so once again, here's how it works. X-rays go in. The electrons absorb that energy and come flying off, and then the machine can detect this combination of how many electrons came off and with what amount of energy. So we get a proportion, or this relationship, we'll look at a graph here in a second, that helps us understand the structure of our atoms. Because they don't all come off with the same amount of energy, which means they're not being held with the same amount of energy as well. It comes down to the binding energy, which is actually a big theme in our lesson today. that this binding energy, the force of a nucleus to its electrons, plays a key role in atoms' behavior and what they do. Okay? This right here is an example of what a photoelectron spectrum can look like. Okay? Where the x-axis is your binding energy, so this refers to how tightly it's held to the nucleus. Okay, binding energy is how tightly it's held to the nucleus. The y-axis is how many electrons have that binding energy. Now, what's weird about these graphs most of the time is, what do you notice about the x-axis numbers?
Because small.
Yeah, it's backwards to normally how it would be. So you got to be careful, because there's other times, depending on where it comes from, where it could be the other way around. So pay close attention to the high end. The higher the energy, the closer these electrons are to the nucleus. So the very first peak, or the highest energy peak, must be always the 1s orbital. The next peak must be the 2s. Now notice that the size of the peaks are the same, because all s orbitals can only hold 2 electrons. Okay? Now this one right after would be the 2p. Notice not a huge jump in binding energy, because they're both part of the second energy level. But between 1 and 2, there's a very big gap of energy. Yeah, Eli.
Well, we have like problems like where we have to like figure out what element it is with that graph.
Yeah, let's do that right now. Good question.
Why, be able to just say, okay, what are they?
No, that's exactly that's what the AP questions will ask, is they'll show you a graph a lot of times, and you should be able to identify the element from its PES spectrum. Yeah, Sam.
So like the one on the previous slide,
Yeah.
from the biggest to the smallest number, why is that one from the smallest to the biggest?
That's what's weird. I cannot find a uniform way. Like this one goes the other way, right? So if we look at this graph, this is 0, that's 10. So this peak would be my 1s peak. So label that on your paper. So you just gotta check your axes to see the way it's set up. But I've actually always wondered that too, Sam, of why there's not like a universal accepted way to do it. So if this is my 1s, then this would be my 2s. Now notice this, kind of going with Eli's question. Since my 2s is half the size of my 1s, what does that tell you?
There is no.
Good, Macy. So the configuration is 1s2, 2s1. And then by knowing a configuration, you can identify the substance.
What's up with you?
Wait,
And it's lithium.
Why would it be 1s2 and only 2s1? When it shows right there, there's only 1 electron.
Oh, so this actually,
That's just
is that what you're
like-
saying?
Yeah.
So this is saying how many electrons. So this is a flipped energy one, right? So this is higher in energy than this one. So I know that this peak has to be my 1s peak. Because the 1s peak is always the one with the most energy. So this graph is mirrored of the last one. So,
1s.
questions on that? Okay, so once again, key thing is you're looking for the one with the highest binding energy is where you start the build. And then you can label it, and then by the peak size, we can identify how many electrons are in that particular orbital. The lower the binding energy, the farther electrons goes away that they are, and most of the time that's referring to their valence and why they're willing to give them away is because their binding energy is so low. Okay, for smiley face, try this question. Ready, set, go. Show me what you put. No, just spinning it like Russian roulette, right? Just take your chances. Oh my gosh. I think you almost all got it right. We're really, really close. Okay, so the correct answer is B, aluminum. Okay, so 1s, 2s, 2p, 3s, And since it's shorter than the S, I know there's only one electron, so you just go to where 3p is located. This is the 3p row, so that's how I know it's aluminum. Okay? All right, show me your answer to the next one, please. Why does it not want to go to the next one? There we go. Okay. Show me your answer, show me your answer, and good job. See, everyone have a smiley face. Good job. Questions on PES spectrums?